Okay, we will now solve our first example for Newton's law of cooling. Very practical example. You take an ice cream out of the freezer, kept it at negative 18 degrees Celsius. Outside it is 32 degrees Celsius. After 1 minute, the ice cream has warmed to negative 8 degrees Celsius. What is the temperature of the ice cream after 5 minutes? So actually, all the given data are what we call our boundary conditions or initial conditions in order to solve our particular solution given the general solution of the differential equation for Newton's law of cooling. As we have discussed last time, uh, the the formula for Newton's law of cooling is T equals the temperature of the surrounding, which is A or T sub S, and then plus C e to the power of K T. But we have also discussed that C is simply equal to the difference between the temperature of the body and the temperature of the surroundings. So that is, the problem says that you take an ice cream out of the freezer, kept it at negative 18 degrees Celsius. So the freezer temperature is negative 18 degrees Celsius. That is also the temperature of the ice cream. Okay, that is also the temperature of the ice cream when it was taken out. So we assume that the temperature of the freezer is at negative 18 degrees Celsius, but that is not necessary because as long as we know the initial temperature of the ice cream is at negative 18 degrees Celsius. That is at T is equal to A. So that is the temperature at T equals 0. The temperature of the ice cream or the body, the initial temperature, is equal to negative 18 degrees Celsius. Right? So we obtain our C now. Recall that C is simply equal to the temperature of the body minus the temperature of the surrounding. And it is stated here that the temperature outside is 32 degrees Celsius. So that is now the temperature of our atmosphere, of our surroundings. So C is equal to negative 18 minus the temperature of the surrounding, which is at 32 degrees Celsius. So we have negative 18 minus 32, which is negative 50. So that is our C. Now we have more particular a solution that is that has a value for C already. So we can rewrite our equation as T equals A, and the temperature of the surrounding is 32, plus C is now equal to negative 50. Okay, so let me change the eraser size. So sorry, this is negative 18 minus 32, so that is negative 50. So T is equal to negative 30, that is positive 32, the temperature of the surrounding A, then plus, supposed to be plus CE to the power of KT, CE to the power of KT, but since C is equal to negative 50, so we write minus 50, E to the power of KT. KT. Okay, so we can see that we only have, at first we have many unknowns But here we only have two unknowns, the k and the t. All right. So next given is at t is equal to, it is stated that after 1 minute, okay, after 1 minute, the ice cream has warmed to negative 8 degrees Celsius. So after 1 minute, t is equal to 1. The temperature of the ice cream now is equal to negative 8 degrees Celsius. Right? So it is already near melting. So t is equal to 1, t is equal to negative 8 degrees Celsius. So we substitute it to negative 8, we substitute it to t, the temperature of the ice cream. So negative 8 equals the temperature of the surrounding, 32. Okay, the temperature of the surrounding. Sorry. The temperature of the surrounding is 32. Okay. Minus 50 e to the power of k, and t, the time, is equal to 1. Okay. So it is very obvious that we have to obtain our k, the value for our k, the proportionality constant in this equation. So we transpose negative 32 to the other side. 32 to the other side, it becomes negative 32 equals negative 50 e to the power of k. And then negative 8 minus minus 32 is equal to negative 40 equals negative 50. Negative 50 e to the power of k. And we divide everything by negative 50. So we have negative 40 over negative 50 equals e to the power of k. Of course, negative 40 divided by negative 50, at its lowest term, is 4/5. Negative cancels, and this is e to the power of k. This time we will take the natural logarithm of both sides so that we can cancel, we can obtain k. So ln of 4/5 equals ln of e to the power of k. Okay. So we have k, finally we have k equals ln of 4/5. Alright? So k is equal to ln of 4/5. Then we go back to our main equation now that we have obtained already our k. So our main equation is t equals 32 minus 50 e to the power of kt. 32 is our temperature of our surrounding. 50 is our negative 50 is our c. Our k now is equal to ln of 4/5, okay, times t. All right. So we know that this is times t. We know that e to the ln of 4/5 becomes 4/5, right? So how do we extract t? That is, we simplify. T is equal to 32 minus 50, okay, 50 times e to the power of ln of 4/5, times raised to the power of t. Okay, we raise it to the power of t. Okay. So t, the temperature of the ice cream, is equal to 32 minus 50. And e to the ln of 4/5 we know is 4/5. Okay. Raised to the power of t. And then the problem says, what is the temperature of the ice cream after 5 minutes, after 5 minutes. So that is at T equals 5 minutes, what is the temperature of the ice cream T? So after 5 minutes, T is equal to, we simply substitute 5 to T, 32 minus 50. Okay, 50 times, this is minus 4/5, raised to the power of 5. 5 does not cancel because this is an exponent. So 4/5 raised to the power of 5 times 50, and the answer to that is subtracted from 32, and the temperature of the ice cream after 5 minutes is 15.616 degrees Celsius. So of course, we know that this is not realistic because by this time the ice cream must have melted already, but it's just application of we are just trying to apply the Newton's law of cooling, and we know, of course, that you do not have 5 minutes before using Newton's law of cooling. We can say that you do not have 5 minutes in order to eat all of the ice cream, because after 5 minutes it would have liquefied already. Its temperature is 15.616 degrees Celsius. Using this formula for Newton's law of cooling, you can, if the melting point of the ice cream, let's say, is 0 degrees Celsius, then you can find the time before the ice cream reaches the temperature of 0 degrees Celsius, and by the time you have to eat all of the ice cream already. So very practical example using our Newton's law of cooling. Right? So we will be studying more about Newton's law of cooling using some other examples in our next video.